Warm welcome, everybody. Thank you for being here. Get yourself ready with a notebook, grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. Today we look at problem 5, free response problem 5. As we continue looking through the non-calculator problems from the 2025, that was this year, the AP Calculus AB exam. So far we've seen a couple of easy problems. We've seen some parts or questions that are not the easiest. This one ranks somewhere in the middle, I would say. If you want to relive your experience, maybe you already took the exam, go ahead and take 12 or so minutes to try to solve this through and through. If you didn't get to it on the exam, but now you have the chance to, there's a little bit less time pressure, obviously. Then when you're ready, come back, see how we did it here. Okay, let's get started. So we have two particles, H and J. They're moving. And we're looking at the time frame from 0 to 5. The position of particle H is given, so this tells us where the position of the particle is, where it's located. And then we're given the velocity of particle J. So this is telling us how fast that particle is moving. It's not telling us where it's at. It tells us how fast it's moving. Okay, part A, very easy. Find the velocity of particle H at t equals 1. So we basically want VH of 1. But first we need VH. VH is simply going to be the derivative of XH. So we're going to have e to the t squared minus 4t. That stays the same. That's the rule for e. And then we multiply by the exponent derivative, 2t minus 4. And if they want us to plug in 1, then we say the velocity of particle H at 1 is e to the 1 minus 4 power times 2 minus 4. So that sounds like negative 2 e to the negative 3. If you'd like, you can put negative 2 over e cubed. Now we don't really need units here. They don't give us units. But it would just be units per unit of time, some distance over time. And that's the work that leads to our answer. So we get full points for that. All right, part B. During what open intervals of time from 0 to 5 are particles H and J moving in opposite directions? Okay, now this is quite an interesting question. Open intervals, that's what we're looking for, between 0 and 5. And we need them to be moving in opposite directions. So the best way to analyze this kind of stuff is with a chart. We want to analyze their velocities. So we're going to make a chart. Let's remind ourselves that VH is simply, if I rewrite it a little bit, 2t minus 4 times e to the t squared minus 4t. So I kind of have a factored form for my velocity of h. And then, of course, v of j, so the velocity of object j, they gave us this equation. It's simply 2t times t squared minus 1 cubed. Okay, now t squared minus 1 might seem a little tricky, but you can just think of it as t minus 1t plus 1. And this is all cubed. So let's use a chart. This is a perfect example of when the chart comes in handy. Here's our time, and we have some important times along the way. We have some important times when VH is 0, Now this can only equal 0 when t equals 2. This is always going to be positive here. E to any power is always positive. Even if it's a negative power, it's still a positive value. So that's helpful to know. That means that 2 is going to be on this number line somewhere. And then if we look at Vj, we have special values at 0, 1, and -1. We really don't need to consider 0 or -1, but I'll throw them on the chart anyways. -1, 0, 1, and 2. And what we're going to do is we're going to plot our factors of VH. So we're going to have e to the t squared minus 4t. This is always a positive, never 0. And then we have our other factor, 2t minus 4. This is 0 when t equals 2, and it's negative everywhere else. So that means that the velocity overall for h simply follows the pattern negative, negative, then it hits 0, and then we go positive. Now, if we plot the factors of Vj, we'll have 2t. That, of course, is 0 when t is 0. Negative before, positive after. Then we have t minus 1. And this is cubed, so it's going to have the exact same behavior as t minus 1 because it's an odd degree. And similar story with t plus 1 cubed, except it is 0 at -1. Now, if we take these three into account, altogether we get Vj of t. So we end up with 0, 0, 0, negative, positive, negative, positive. Here's the kicker. We don't really need these rows anymore. We're just comparing the velocities. We're just comparing the velocities at this point. But additionally, we don't need anything before time equals 0, so we really don't need any of this. I know it's kind of disgraceful, perhaps blasphemous, one might say, to be scribbling off portions of the chart that we just worked so hard to get. But the chart is only for us to use as a tool. So looking from here, now we can keep track of when they're opposite signs. At t equals 1, in fact, we can just multiply them and see when their product is negative. We would get a plus, then a 0, then a negative, then a 0, then a plus. So they have opposite sign in between 1 and 2. So we would say on the interval from 1 to 2, Vjt and Vh of t have opposite signs. So that means that the particles are moving in opposite directions because one's velocity is like a positive and one's velocity is a negative, or vice versa. It doesn't matter. They're just opposite of each other. Okay, so there's the reason for our answer. Pretty nice there. Part C, it can be shown that the velocity of j, I think it says Vj prime. Vj prime of 2 is greater than 0. Is the speed of the particle increasing, decreasing, or neither? I really think that's saying Vj prime. So first let's find out what Vj prime is, I guess. It's asking if the speed, okay, got it. So it's already telling us that the acceleration aj of 2 is positive. So in order for us to determine if the speed is increasing or decreasing, we have to see whether or not the velocity and the acceleration are both pointing in the same direction, or opposite directions. Because if the velocity and acceleration are pointing in opposite directions, then the speed will be decreasing, right? If you're moving forward but something is literally pushing you backwards, you will be slowing down. Whereas if you're moving backwards and something's pushing you in that backwards direction, let's say you're running backwards and then someone pushes you even further, then you're going to be speeding up, right? Or if you're running forward and someone pushes you forward, you're going to be speeding up because your velocity and acceleration agree. So let's check if the velocity and acceleration agree. It's pretty easy to do that with a sign chart here. So Vj is already down here. We know that Vj at 2 is a positive. Oh, Vj at 2 is actually 0, isn't it? No, it's a positive. It's a positive. Yeah, sorry, my apologies. Vh of 2 is 0. Vj of 2 is a positive. So according to the chart, I mean, we can just say that here, Vj of 2 is also positive. I mean, if you wanted to plug it in, you totally could. Right? We have an equation for this. So we could say that Vj of 2 is, it's 4 times 2 squared is 4 minus 1 is 3. So it's 108, which is definitely positive. So the velocity is positive and the acceleration is positive. That one's easy. So it's increasing speed. Nice. Final part D. Particle J is at position x equals 7 at time t equals 0. So they're giving you this initial condition. Find the position of the particle at t equals 2. We're going to have to use the fundamental theorem of calculus for that. So in order to take particle J and get its position, we need the velocity, and then we have to take the integral of the velocity. So we say the integral from 0 to 2 of the velocity of J is going to be equals to x of 2 minus x of 0. Alright, so that means that the integral from 0 to 2 of 2t t squared minus 1 cubed dt, and then plus x of 0, if I add it to both sides, right? If I add this x of 0 to both sides, then that leaves me with x of 2, which is my goal. Find the position of the particle at 2. So we just have to do an integral here. We just have to u sub. It's not too bad of a u sub. But we do have to change our u limits. So instead we're going to go from -1 to 3, and then our du is already covered there because our du is just going to be 2t dt. So this is going to turn into the integral from -1 to 3 of u cubed du plus x of 0, which they told us was 7. And now we just anti-differentiate. U to the 4th over 4. Evaluate this from -1 to 3 and add 7 to it. That's pretty easy to do. So we have 81 over 4 minus positive 1 over 4. And then plus 7, which is 80 over 4 plus 7, which is 20 plus 7, or 27. Okay, we don't really have any units there, but we just have the final position. And that's because the integral shows us how far displaced the thing is. It doesn't tell us the exact distance that it traveled, but it tells us the change in its position overall. And if we started at position 7 and we're changing our position by 20, we end up at 27, of course. No surprise there. Okay, so this one, yeah, I would say it's somewhere in the middle. I wouldn't say it's the easiest question, but it's also not the most difficult. The hardest part for me was reading whether or not that was a prime. I'm assuming that was a prime. If not, you can just show that the acceleration is positive anyways. Okay, so they mixed a little bit of integration and as well a little bit of differentiation so that you can interpret increasing, decreasing behavior. This question B was a little bit interesting. You have to find out where they're moving in opposite directions. And when you have factorization or factorizable polynomials and functions, the chart is just the way to go. Put some respect on the name. The chart. Put some respect on the name. The chart. That's THE. Chart. All right, that's enough blab out of me. I'll see you guys next time.